A futuristic aircraft emerged during World War II, as the skies above Europe became a battlefield. The Messerschmitt Me 163 Comet was the world's first rocket-powered interceptor aircraft. With a terrifying speed of 702 miles per hour and the ability to reach 30,000 feet in less than 3 minutes, the Me 163 broke aviation boundaries and brought with it stories of daring and unimaginable innovation in war. But greatness did not come easily. Its dangerous fuel system and challenging controls turned the aircraft into a contradictory legend, both a source of pride and terror for those who flew it. This is the story of the Me 163, a symbol of courage and innovation, but also a warning about the price of pioneering. Revolutionary design features of the Me 163. The engineering brilliance of the Me 163 stemmed from its groundbreaking design philosophy. Dr. Alexander Lippisch's innovative approach merged advanced aerodynamics with rocket propulsion, creating an aircraft that redefined the boundaries of flight technology. The Me 163 distinctive tailless design incorporated swept wings at precisely calculated angles. The leading edge featured a 27-degree sweep at the root, gradually increasing to 32 degrees toward the tips. This configuration served dual purposes, reducing drag at high speeds and maintaining stability without a conventional tail. The wing design stemmed from extensive glider research, incorporating integrated leading edge slots positioned directly forward of the 11 control surfaces. The aircraft's propulsion system marked a significant departure from traditional aircraft engines. Engineers at Messerschmitt integrated the Walter HWK 509A2 rocket engine, generating 3,748 pounds of thrust. The power plant's integration required innovative solutions for fuel storage and management. A small propeller mounted in the nose drove the generator, ensuring electrical power for critical systems during flight. The control system of the Me 163 was a remarkable example of engineering brilliance, combining simplicity with effectiveness in a way that few aircraft of its time could match. Its design was centered around ensuring optimal control at extreme speeds and altitudes, while remaining functional and reliable in challenging conditions. One of the key innovations was the use of hydraulically actuated 11s, which provided highly precise control over the aircraft's pitch and roll, a crucial feature for a rocket-powered interceptor. These 11s allowed pilots to maneuver with accuracy, even at the Me 163 extraordinary speeds. Additionally, the aircraft was equipped with integrated leading-edge slots that enhanced its low-speed handling. This feature was vital for maintaining stability and control during takeoff and landing, where the Me 163 high speed could otherwise make it difficult to manage. To further improve its performance during these critical phases, the Me 163 incorporated ground effect compensation systems. These systems helped to counteract the turbulence and instability caused by the proximity of the aircraft to the ground, ensuring smoother and safer landings despite the challenges posed by its unique design. The control system's sophistication became apparent in its handling characteristics. The Me 163B demonstrated remarkably docile landing behavior, primarily due to its advanced leading-edge slots. Furthermore, the aircraft maintained excellent controllability at high speeds, incorporating a Mach warning system to prevent control loss during rapid acceleration. The engineering team addressed stability challenges through meticulous balance of the center of gravity and lift positions. Consequently, the aircraft neither stalled nor spun, maintaining controlled flight even in extreme conditions. The design's effectiveness manifested in its exceptional maneuverability, allowing pilots to execute precise intercept missions despite the aircraft's unprecedented speed capabilities. The integration of these revolutionary features resulted in an aircraft that could climb to 39,500 feet while maintaining exceptional agility. Specifically, the combination of rocket propulsion and advanced aerodynamics enabled the Me-163 to achieve remarkable performance metrics without compromising structural integrity or pilot control. The heart of the beast, Me-163 rocket engine. At the core of the Me-163 exceptional performance lay the Walter HWK-109-509 rocket engine, a pioneering achievement in propulsion technology. This innovative power plant marked a significant advancement from earlier rocket designs, establishing new benchmarks in aircraft propulsion. The Walter HWK-109-509 was a highly advanced bipropellant rocket system developed by Helmuth Walter Kommanditgesellschaft in 1943. This engine was capable of delivering variable thrust, ranging from 330 pounds to 3,750 pounds. The engine's design was a masterpiece of innovation, featuring several key components that contributed to its exceptional performance. The primary combustion chamber, known as the Hauptofen, was responsible for generating the initial thrust, while the secondary chamber, or Marskofen, provided additional power during cruise operations. The system also included an integrated turbopump, which ensured a steady and efficient flow of propellants into the engine, along with a steam-driven mechanism for propellant delivery. This complex design allowed the engine to reach peak thrust levels of approximately 3,820 pounds of force, enabling the aircraft to achieve impressive speeds and climb rates that were unmatched at the time. The Walter HWK-109-509 was a key factor in the extraordinary performance of the Me-163, providing the necessary power to propel it to the limits of aviation technology. The propulsion system utilized two primary components, T-Stoff oxidizer and C-Stoff fuel. The T-Stoff consisted of 80% concentrated hydrogen peroxide. Additionally, the C-Stoff combined 30% hydrazine hydrate, 57% methanol, and 13% water. The propellant management system incorporated specialized aluminum tanks for T-Stoff storage and enamel or glass-lined containers for C-Stoff. The engine's steam generator employed a wire mesh catalyst to decompose T-Stoff, powering the turbopumps. This arrangement ensured efficient propellant delivery throughout the flight envelope. The system maintained operational efficiency through careful separation of components, preventing uncontrolled reactions between the volatile substances. The thrust control system featured sophisticated mechanical and hydraulic components. The engine incorporated 4 distinct power settings, ranging from idle to full climbing power. A single turbine, driven by catalytically decomposed T-Stoff, powered the propellant pumps. The B and C series engines introduced an advanced dual-chamber configuration. The smaller Marskofen chamber, generating approximately 400 kilograms force, provided efficient cruise power. This innovation extended flight endurance from 8 to 12 minutes, marking a 50% improvement in operational capability. The engine's control system addressed earlier throttling challenges through precise fuel management. Initially, the RLM demanded throttle capability, leading to the development of 2-setting turbopumps. Although throttling reduced fuel economy, subsequent design iterations optimized performance through the dual-chamber configuration, eliminating the need for main chamber throttling. Engineering challenges and solutions. Developing the Me-163 presented engineers with unprecedented technical hurdles that demanded innovative solutions. The aircraft's unique combination of rocket propulsion and tailless design created complex engineering challenges requiring groundbreaking approaches. The Me-163 aerodynamic stability posed significant engineering challenges. The aircraft exhibited marginal lateral stability, requiring careful design considerations. Engineers addressed these issues through integrated leading-edge slots positioned directly forward of the 11 control surfaces. The stability solution proved so effective that test pilot Heinrich Dittmer declared, "It just won't spin." Accordingly, the design team implemented a Mach warning system to prevent control loss at high speeds. This addition became essential as the aircraft's exceptional thrust-to-drag ratio made it challenging for pilots to detect the onset of severe compressibility. The volatile nature of the Me-163 propellants imposed stringent material requirements, presenting engineers with significant compatibility challenges. T-Stoff necessitated the use of aluminum tanks to prevent corrosion and spontaneous combustion, while C-Stoff required storage in glass or enamel-lined containers to avoid adverse chemical reactions. Pilot flight suits were constructed from synthetic polyvinyl chloride to ensure chemical resistance. Additionally, the engineering team implemented strict material handling protocols, including maintaining a minimum separation distance of 800 meters between fuel trucks to mitigate the risk of catastrophic chemical reactions between the propellants. The engineering team implemented sophisticated weight reduction strategies throughout the aircraft. The empty weight of 3,197 pounds increased to 5,291 pounds when loaded with 140 gallons of propellants. Subsequently, engineers developed several key solutions. The wings incorporated a lightweight construction using two spars covered in 8 mm thick fabric. The fuselage design featured numerous removable panels, enabling quick access for maintenance while minimizing structural weight. Indeed, the aircraft's landing gear system exemplified this approach through its jettisonable main wheels and retractable skid mechanism. The weight optimization extended to operational procedures. Following takeoff, pilots would jettison the wheeled dolly to reduce drag and conserve fuel. This strategy, combined with the aircraft's efficient aerodynamic design, enabled the Me-163 to achieve remarkable performance despite its limited fuel capacity. Dangerous chemistry. The Me-163 fuel system. First of all, the Me-163 fuel system represented one of the most hazardous aspects of aircraft engineering, utilizing a combination of highly reactive chemicals that demanded extraordinary precautions. The propulsion system relied on two primary components, T-Stoff oxidizer and C-Stoff fuel, which reacted violently upon contact. T-Stoff consisted of 80% hydrogen peroxide with trace amounts of stabilizers, ink. This powerful oxidizer demonstrated extreme corrosiveness toward most materials, particularly organic substances. C-Stoff, primarily a mixture of methanol, hydrazine hydrate, and water, presented its own set of challenges. These substances qualified as hypergolic propellants, meaning they would spontaneously ignite when mixed at normal temperatures. The volatile nature of these chemicals necessitated specialized storage solutions. T-Stoff required aluminum tanks to prevent corrosion, whereas C-Stoff demanded glass or enamel-lined containers. The main T-Stoff tank held 1,040 liters, with two auxiliary tanks of 120 liters each positioned within the lower flanks of the cockpit area. In particular, the C-Stoff fuel tanks were strategically placed in the aircraft's wings. The engineering team designed and implemented stringent safety protocols to manage the hazardous substances involved. These measures included maintaining a minimum separation distance of 800 meters between fueling crews and trucks, conducting thorough decontamination procedures between fueling operations, utilizing specialized testing systems to prevent cross-contamination, and employing water-based neutralization systems for use in emergencies. Primarily, pilots wore specialized protective gear, including acid-resistant flight suits. As a result of the extreme dangers, ground crews known as black men for their protective uniforms followed strict handling procedures. The fuel system incorporated multiple safety features, yet accidents still occurred. Therefore, engineers developed a complex testing system to ensure proper fuel identification, as both substances appeared visually similar. The engineering team faced constant challenges with the fuel lines and fittings, which often failed in unpredictable ways. Even minor leaks during hard landings could trigger catastrophic reactions. The system required thorough flushing with water before and after each flight to remove any residual propellants, establishing a new standard in aircraft maintenance protocols. Innovative landing gear solutions. Unique engineering solutions characterize the Me-163 unconventional landing gear system, which departed radically from traditional aircraft designs. The necessity for lightweight construction led engineers to develop an innovative two-part landing system that prioritized performance over conventional comfort. Engineers developed a specialized two-wheel dolly system for takeoff operations. The production B-series aircraft utilized a cross-beam axle dolly design, replacing the earlier sprung independent suspension system that had caused problems during testing. This modification became essential after prototype trials revealed that the original well-sprung dollies would rebound upon takeoff, potentially striking the aircraft's underside. Primarily, all takeoff operations required strong headwind conditions, as the rudder remained ineffective until the aircraft achieved sufficient speed. The dolly system, lacking both shock absorption and steering capabilities, necessitated operations from wide grass fields rather than concrete runways. The landing system incorporated an extendable skid mechanism with an oleopneumatic strut, designed to absorb both ground-running impacts during takeoff and landing forces. Throughout landing operations, pilots maintained speeds around 220 kilometers per hour, with no opportunity for second attempts due to the unpowered approach. The engineering of the skid posed several operational challenges, including deployment failures that often caused pilot injuries, the risk of aircraft overturning on soft ground, the necessity for precise execution of touchdowns due to high landing speeds, and frequent skid failures that resulted in spinal injuries for pilots. The Schutzschlepper, a specialized recovery vehicle, represented an ingenious solution for aircraft retrieval. This converted agricultural vehicle featured a unique design specifically engineered for the Me-163 recovery operations. The vehicle's configuration included: the retrieval system employed twin trailing lifting arms that elevated the aircraft from under each wing. Throughout its development, engineers tested alternative recovery methods, including an experimental system utilizing sausage-shaped airbags for aircraft lifting. Essentially, Schutzschlepper's design incorporated a pivoting retrieval trailer equipped with twin continuous track setups, enabling efficient aircraft recovery across various terrain types. This recovery system proved crucial since the Me-163 remained immobile after landing, making it potentially vulnerable to enemy aircraft. The engineering team ultimately developed plans for implementing a parachute-assisted landing system to reduce airfield length requirements. Hence, later variants, such as the Me-163D, incorporated a retractable tricycle landing gear consisting of a smaller forward wheel and two larger rear wheels positioned below the wing roots. Flight control systems. Advanced control systems formed the backbone of the Me-163's remarkable maneuverability. The aircraft's sophisticated flight control architecture, combined innovative hydraulic systems with precisely engineered control surfaces. The Me 163 hydraulic system incorporated an oleopneumatic design that powered critical control functions. Primarily, the system managed the aircraft's unique 11 surfaces, which served dual roles as both elevator and aileron controls. The hydraulic mechanisms enabled precise control inputs, even at speeds approaching 702 miles per hour. The system incorporated hydraulically operated wing flaps to enhance landing control, oleopneumatic shock absorption for the landing skid, pressure-regulated mechanisms for control surface actuation, and integrated backup systems to ensure functionality during emergencies. The control surface design marked a significant departure from conventional aircraft configurations. The Me 163 wings contained two primary spars covered in 8 mm thick fabric. Simultaneously, the trailing edges housed specially designed ailerons that provided both pitch and roll control through a sophisticated mixing system. The 11 system demonstrated remarkable effectiveness, allowing pilots to maintain precise control throughout the flight envelope. Altogether, the aircraft's control surfaces remained responsive even during unpowered gliding phases, enabling smooth transitions between powered and unpowered flight. The cockpit interface incorporated innovative features to improve pilot control, including a ram air turbine mounted on the nose to generate electrical power for essential systems. This setup provided power to the Fuji-16ZE radio transmitter and receiver, the direction finder and compass systems, the reflector gun sight, and the cockpit instrumentation lighting. The airspeed indication system utilized dual sources, combining readings from both the pitot tube on the port wing's leading edge and a secondary inlet in the nose. Straightaway, this arrangement provided pilots with accurate speed data throughout the flight envelope. The system also supplied pressure information to the rate of climb indicator. The Me 163 control interface proved remarkably intuitive, allowing pilots to execute precise maneuvers without excessive physical effort. Generally, the aircraft demonstrated exceptional stability, refusing to enter spins even under extreme control inputs. The integrated leading edge slots positioned forward of the 11 control surfaces contributed significantly to these favorable handling characteristics. The pilot's control stick directly actuated the 11s through the hydraulic system, providing immediate response to input commands. Ultimately, this arrangement allowed for exceptional maneuverability while maintaining stability at both high and low speeds. The control system's effectiveness became particularly apparent during landing approaches, where pilots could maintain precise control even during unpowered descents. Performance engineering. Performance metrics of the Me 163 Komet established new benchmarks in aviation history. The aircraft's remarkable capabilities stemmed from its meticulously engineered systems and innovative design approach. The Me 163 speed capabilities redefined aerial combat parameters. German test pilot Heini Dittmer achieved an unofficial speed record of 1,130 kilometers per hour in early July 1944. Undoubtedly, this record remained unmatched by turbojet-powered aircraft until 1953. The aircraft's remarkable velocity was achieved through advanced engineering features. Its maximum speed reached 960 kilometers per hour at cruise settings, with an operational ceiling of 39,500 feet. The takeoff speed threshold was 320 kilometers per hour, while the optimal climbing velocity was 676 kilometers per hour. The Me 163 vertical performance capabilities markedly distinguished it from contemporary aircraft. Primarily, the rocket-powered interceptor demonstrated unprecedented climbing abilities. The aircraft could reach 12,000 meters in merely 3 minutes. Comparatively, this climb rate surpassed all other World War II fighters. The engineering team achieved these results through precise thrust-to-weight ratio optimization and aerodynamic refinements. The climb profile followed a specific pattern, maintaining level flight at low altitude until reaching optimal climbing speed, then executing a 70-degree angle of climb. The exceptional performance capabilities necessitated significant operational compromises. The Me-163 powered flight endurance remained limited to 7.5 minutes, evidently constraining its operational radius. This duration represented approximately 25% of the flight time available to contemporary jet fighters like the Heinkel He-162A Spats. The engineering team addressed these limitations through strategic performance optimization. The aircraft's thrust control allowed for variable power settings, enabling pilots to manage the critical balance between speed and endurance. Nonetheless, the maximum operational range extended to only 80 kilometers during the 7.5-minute powered flight time. This constraint influenced tactical deployment strategies, requiring careful planning of intercept missions. The thrust-to-drag ratio presented unique challenges for pilots. While the aircraft demonstrated remarkable agility and handling characteristics at high speeds, the rapid acceleration could lead to control difficulties. The engineering team incorporated specific safety measures to prevent loss of control during severe compressibility conditions. Flight testing revealed additional performance characteristics that influenced operational parameters. The aircraft accelerated so rapidly that it frequently exhausted its fuel supply before reaching maximum velocity potential. This limitation prompted the development of alternative tactical approaches, including high-altitude towing operations to conserve fuel for combat maneuvers. The performance envelope expanded through systematic testing and refinement. Dawn Aerospace's testing protocols established new benchmarks for climb rate verification, with the aircraft ascending from ground level to 66,000 feet in 118.6 seconds. These achievements validated the fundamental engineering principles employed in the Me-163 design, while simultaneously highlighting the operational constraints in He. Engineering legacy. Technical achievements of the Me-163 Komet shaped numerous aspects of modern aviation engineering. The aircraft's pioneering designs and solutions to complex engineering challenges established foundational principles for future aerospace development. The Me-163 influence extended far beyond its operational lifespan. The aircraft's delta wing configuration and rocket propulsion system established new parameters for high-speed flight. Test pilot Heine Dittmer's achievement of 1,130 kilometers per hour in July 1944 remained unmatched by turbojet-powered aircraft until 1953. Primarily, this accomplishment validated the effectiveness of swept-wing designs at high speeds. The aircraft's aerodynamic innovations influenced post-war aviation development across multiple nations. The United States, Soviet Union, United Kingdom, and France captured Me-163 Komets, developing their rocket-powered interceptor prototypes. Besides, the Japanese aerospace industry received technical documentation, leading to the development of their variant, though the actual pattern aircraft never reached Japan. The development of the Me-163 offered invaluable lessons that significantly influenced modern aerospace engineering. Its innovative design, combining rocket propulsion with principles of traditional glider construction, underscored the necessity of balanced engineering approaches. This harmony between advanced propulsion systems and aerodynamics led to exceptional thrust-to-drag ratios and handling characteristics, setting new standards for the design of future high-performance aircraft. The program emphasized several critical engineering principles. It highlighted the importance of selecting advanced materials that could withstand the extreme chemical environments of the propellants used, ensuring both safety and functionality. The integration of robust safety systems into the aircraft's design demonstrated the need for meticulous attention to risk management in high-performance aviation. Furthermore, the project illustrated the delicate balance required between maximizing operational performance and maintaining practicality in real-world use. Finally, it reinforced the value of comprehensive testing protocols to refine and validate designs, a practice that has since become a cornerstone of aerospace engineering. The Me-163 technical contributions to aerospace engineering proved substantial. The aircraft's sophisticated control system, coupled with its innovative propulsion technology, established new standards in aviation design. The development of the Walter HWK-109-509 rocket engine, generating 3,748 pounds of thrust, demonstrated the feasibility of rocket propulsion for air. The engineering team's solutions to complex technical challenges influenced future aircraft development. The implementation of leading-edge slots, positioned directly forward of the 11 control surfaces, demonstrated effective methods for maintaining stability in tailless aircraft designs. Thus, these innovations contributed to the evolution of modern flight control systems. The Me-163 fuel system engineering, analogous to modern rocket designs, established crucial safety protocols. The development of specialized handling procedures and protective equipment for volatile propellants set standards for hazardous material management in aerospace applications. Ultimately, these safety protocols influenced modern rocket fuel handling procedures. The aircraft's performance capabilities redefined the boundaries of aerial combat. The ability to climb to 39,500 feet while maintaining exceptional maneuverability demonstrated the potential of rocket propulsion in military aviation. Certainly, these achievements influenced the development of subsequent interceptor aircraft designs. The engineering legacy of the Me-163 extends into contemporary aerospace applications. The aircraft's integrated leading-edge slots and advanced control surfaces established principles still relevant in modern aviation. The development of specialized recovery equipment and ground handling procedures contributed to the evolution of aircraft support systems. The Messerschmitt Me 163 Komet remains a groundbreaking milestone in aerospace engineering. With its tailless delta wing design and rocket propulsion, it shattered speed records, reaching an incredible 623.8 miles per hour at a time when most fighters struggled to exceed 400 miles per hour. Despite its limited military impact, the Me-163 technical innovations in safety systems, landing gear design, and flight controls influenced post-war aviation and continue to inspire modern aerospace advancements. What do you think about the engineering breakthroughs of the Me-163? Which aspect of its design do you find most fascinating? Let us know in the comments. If you enjoyed this video, don't forget to give it a like and subscribe to the channel for more insights into aviation history and technology. Thank you for watching.